Pluto is a mysterious dwarf planet that lives far away. Once belonging to our solar system's planetary group, recent unexpected announcements made by prominent astrophysicists, including Neil deGrasse Tyson, have brought Pluto back into the spotlight, thanks to a shocking discovery. They suggested that the icy world is on a possible path of collision with Neptune. However, what caused this? And what would happen if this were to occur? Are we witnessing a massive, rare phenomenon in astronomy, or is there more to this cosmic looming clash? Join us as we investigate the possibility of an impact between Pluto and Neptune. Pluto was once classified as a planet, but was partially reclassified as a dwarf planet because of its unusual orbit. It remains a subject of interest and investigation in the community of astronomers. According to leading scientists' most recent predictions, Pluto's path is dangerously close to Neptune's, with Neil deGrasse Tyson and others sounding the alarm concerning a potentially dangerous collision between these two celestial bodies. This event might constitute a serious threat to Earth. What makes such an event even conceivable? In contrast to other planets, Pluto's orbit around the Sun takes an incredible 248 years to complete one revolution, meaning that since its discovery in 1930, it hasn't even completed one full orbit. However, the fascination does not end there. Pluto's highly elliptical orbit, marked by significant gravitational influences, departs dramatically from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its angle of inclination. Its path is tilted at 17 degrees to the ecliptic plane, making Pluto's trajectory much steeper than those of other planets. This tendency, combined with its elliptical nature, adds layers of complexity to its orbital pattern. One of the most fascinating features of Pluto's orbit is where it intersects Neptune's path. For approximately 20 years in each orbit, Pluto actually approaches the Sun closer than Neptune, defying expectations based on their positions in the solar system. As a result, a natural question arises: why has Pluto not collided with Neptune? The solution lies in the gravitational effects of other planets. Soon after Pluto was discovered, astronomers began researching its unique path. Unlike other planets, with orbits relatively close to the ecliptic plane, Pluto's path stood out due to its steep slope and elliptical shape. The mystery deepened when it became clear that Pluto's orbit actually crosses Neptune's. Pluto's orbital stability amidst these complexities is evidence of the intricate nature of space mechanics. The three-body problem in space involves calculating how objects like the Sun, Pluto, and Neptune move and influence one another with their gravity. This is akin to predicting where they will go based on their current positions and how they interact. This problem demonstrates how the gravitational paths of Pluto, Neptune, and the Sun interact in an intricate manner. Terms like vibration and latitude are components of the VSSK oscillation. According to astrophysicists, this puzzle explains what holds the planets in their orbits. The term vibration of latitude describes the vertical movement of an object in its orbit. For Pluto, this means that when it is closest to Neptune or any other massive planet, it is located significantly above their orbital plane, adding another layer of defense against potential collisions. Another critical aspect is the VSSK oscillation, named after three scientists, Von, Zippel, and Kai, who researched the motion of celestial bodies. This oscillation explains how three objects, like Pluto, Neptune, and the Sun, interact gravitationally, affecting their movement. In the case of Pluto, the VSSK oscillation helps us understand why its course around the Sun is so unusual. Despite appearing erratic, this oscillation contributes to its smooth operation over a prolonged period. As demonstrated by the VSSK oscillation, even though space seems chaotic, some patterns and rules maintain order, keeping everything in its proper place. Pluto's orbit is held stable, preventing it from colliding with Neptune. The three-body problem aids in comprehending how these gravitational forces alter the paths of celestial bodies. Studies of Pluto and other distant worlds in our solar system have revealed additional insights. Simulations conducted in the 1980s demonstrated that Pluto's orbit is stable due to these properties. Though technically chaotic, with minor alterations in initial conditions leading to significant variations over millions of years, these distinctive properties maintain equilibrium for extremely long time frames, effectively keeping the peace. Recent computer tests have helped us comprehend how massive planets like Jupiter, Saturn, and Neptune influence Pluto's course around the Sun. There is a special relationship between Neptune and Pluto. For every 2 orbits Pluto makes around the Sun, Neptune completes 3. This connection helps maintain Pluto's path's stability. However, Neptune is not the only contributor. Jupiter's gravity plays a significant role in maintaining Pluto's secure orbit, with Saturn assisting to a lesser extent. These tests demonstrate that Jupiter's gravity alone is strong enough to ensure Pluto follows a steady course for billions of years. It's as if Jupiter, Neptune, and Saturn are all cooperating to keep Pluto moving safely in space without running into problems. These phenomena play a crucial role in maintaining the predictability and order of celestial bodies' actions in the universe. Without these mechanisms, the solar system would be a much more chaotic and unpredictable place. Bodies like Pluto could collide with others or be ejected from their established routes, causing a chain reaction among other celestial bodies. Discussions about the possibility of Pluto crashing into Neptune in the foreseeable future are highly significant. Pluto's orbit reveals the fluid nature of the solar system. Its case illustrates how even the most seemingly unstable orbit can achieve balance through the complex interplay of gravitational forces and orbital mechanics. Additionally, the significance of constant observation and investigation of these phenomena helps us better comprehend our place in the cosmos. Investigating the depths of space frequently leads us to confront the unpredictability of celestial bodies, and Pluto's orbit is an eloquent illustration of this unpredictability. The concept of orbital chaos, which refers to the delicate dependence on the initial conditions of a celestial body's path, is well exemplified in Pluto's case. This indicates that even minor nuances in the dwarf planet's velocity or position can significantly alter its long-term orbit. Using computer simulations, researchers have determined how Pluto moves through space. These simulations rely on intricate mathematics to replicate how Pluto, Neptune, and other space objects gravitationally interact. By adjusting specifics, astronomers can see how small tweaks can have a significant impact on Pluto's trajectory. Simulations that began in the late 1980s revealed an intriguing fact about Pluto's course. Despite factors like latitude and VSSK oscillation maintaining its orbital stability, it remains quite unpredictable. If you begin with only a slight difference in Pluto's location or velocity, its path may ultimately appear very different over many years. However, despite this chaos, Pluto's orbit remains stable for billions of years, meaning that even though it seems chaotic, there is some underlying order. Predicting cosmic occurrences, particularly those involving erratic orbits like Pluto's, presents significant challenges. The inherent unpredictability of these systems indicates that long-term forecasts are often fraught with uncertainties. While numerical simulations offer effective methods for understanding and anticipating the future paths of celestial bodies, they also highlight the limitations of our predictive capabilities. These models rely heavily on the accuracy of initial conditions and the complex nature of the interactions they simulate. Any minor error or oversimplification can result in significantly different outcomes, making precise predictions a difficult task. The chaotic nature of orbits like Pluto reminds us of the changing and dynamic nature of the universe. While we have advanced significantly in understanding space, Pluto serves as an example of how our comprehension of the universe remains limited. Understanding the gravitational effects of massive planets on Pluto's orbit provides valuable information about the broader dynamics of the solar system. It demonstrates how the position and presence of each planet can affect the stability and paths of other bodies within the system. So, why are prominent astrophysicists recently raising concerns about the possibility of Pluto colliding with Neptune, despite all these complex forces working to prevent such an event? Neil deGrasse Tyson, an important and well-known astrophysicist, has made significant contributions to the spread of astronomical knowledge. He offers a unique perspective on the mysteries surrounding the solar system, particularly the fascinating case of Pluto. Best known for his role in Pluto's reclassification from a planet to a dwarf planet, Tyson provides valuable commentary on the public's fascination with the mechanics of the heavens and the uncharted territories of space. As a punishment, but as a necessity, adaptation to our expanding knowledge among the many objects that orbit our sun, the way Tyson approaches the mechanics of space is one of ongoing education and adaptation. He recognizes the difficulties of orbits, like Pluto's, serve as a reminder of how much remains to be discovered in space. The enchantment of these uncertainties, particularly the possible interactions that occur between Neptune and Pluto, highlights the unpredictable and dynamic nature of our solar system. His work emphasizes the fact that the more we learn, the more questions there are regarding space, encouraging us to investigate and refine our comprehension of the universe. Michio Kaku, another well-known futurist and physicist, provides a unique but complementary perspective on space's mysteries, concentrating on the unpredictable forces that make the universe what it is. Kaku is known for his capacity to connect disparate concepts based on science and futuristic visions, which has made him an important voice in discussions about the mechanics of the universe and its broader repercussions for humanity. His perceptions of Pluto and its orbit emphasize the necessity of ongoing observation and sophisticated modeling to recognize and anticipate potential cosmic events. He sees how interactions between celestial bodies are crucial, not just for academics to study, but for the practical implications. Pluto's potential collision with, for instance, Neptune, is not just a theoretical scenario, but a reminder of the constantly changing and chaotic nature of space. Kaku's futuristic perspective inspires us to take into account the broader repercussions of such incidents and their effects on our comprehension of the solar system, as well as the potential demand for space interventions in the future. From his point of view, he emphasizes the significance of being prepared in space for the unexpected. According to his work, the better our understanding of the forces at play, the more prepared we will be to navigate and possibly lessen the negative effects of cosmic happenings. Tyson and Kaku's points of view agree that space is a realm of unending exploration and that, despite its vastness, our current understanding is still limited. Their focus on the requirement for ongoing investigation and advanced modeling highlights the ever-changing nature of space science. They draw attention to the importance of not only comprehending the current state of the universe's mechanics, but also anticipating their potential shifts in the future. The possibility of a collision scenario involving Neptune and Pluto serves as an example of the larger opportunities and challenges in space exploration. It emphasizes the necessity for robust research, advanced technology, and the ability to change our comprehension as brand new information emerges. For Tyson and Kaku, the mysteries of space, as shown by Pluto's orbit, are an appeal to scientific action to maintain the community and humanity as a whole, extending the scope of our knowledge. There is a general consensus in science that, in the not-too-distant future, Neptune and Pluto's orbits will remain stable because of their slow movement, resonance, and a variety of gravitational influences acting on them. As a result, a direct collision between Pluto and Neptune is extremely unlikely. However, the complexities and possible disturbances in orbital dynamics mean that astronomers must keep an eye on and learn more about these celestial bodies to comprehend their behavior over time and any dangers they might present. In contrast, the scenario of a Pluto and Neptune collision is speculative and considered unlikely in light of the current understanding. It emphasizes the significance of ongoing research and advances in observational astronomy technology, such as more advanced telescopes. Likewise, computer simulations and improved models assist astronomers in making predictions and staying informed about the environment and nature of our solar system's constant change. Dyson's perspective on Pluto's reclassification and Kaku's emphasis on the unpredictability of celestial mechanics both underscore the need for ongoing investigation and adaptability in our comprehension of the universe. The possible collision scenario, while bringing attention to the complex and dynamic interactions throughout the solar system, ultimately brings to mind the vast, still new horizons for us in our comprehension of space. Through constant research and observation, we endeavor to uncover these mysteries to ensure our understanding keeps up with the ever-evolving universe. Pluto's study and orbit open up broader discussions about the solar system's stability. This relationship is fascinating because the governing gravitational interaction of every celestial body that makes up our cosmic neighborhood, each moon, dwarf planet, and planet, is in a delicate balance, where their movements and positions interact in ways that occasionally appear paradoxical. This level of complexity challenges our perception of what is stable and unsteady in space. Astronomers continuously confront the difficulty of making long-term predictions of orbital behavior, as even minute adjustments can reverberate throughout space for billions of years. Despite Pluto's apparently unpredictable path, the cosmic forces at work guarantee that these bodies remain in a state of harmony for extremely long periods. However, even small changes in the orbit of a planet or an unexpected gravitational force from another celestial body could potentially alter this equilibrium. A situation like this could change the direction of planets, moons, and even the creation of tiny planets like Pluto, causing ripple effects all over the solar system. Because of this, it continues to be crucial for scientists to keep improving their models and studying the movements of these far-off worlds, ensuring they are ready for any unexpected cosmic shifts that could happen, regardless of how unlikely they may be. This constant observation brings us closer to a more in-depth knowledge of the universe.